Good afternoon, and I hope you are doing very well, you and your family. Um, uh, with regard to the chapter 5, I did mention some points that we need to design or analysis the water distribution network. We said the main purpose for having this kind or this analysis is to see whether we have the criteria that we need to just see whether a network is to be a reliable network or it's a very good network or it's working active. We have to check 2 points. The first one is to see whether the range of the velocities inside in the flow velocity inside the pipes are maintained in a certain limit, which is how much is the limits, Ahmed, for having a reliable water? Let me say a flow in the pipe should be how much? Berham. Um,
Doctor, what was your question?
the question is in a network, when we are going to design or analysis and work, we are working on two things: the velocity of the flow in the pipe and the pressure of the flow in the network, in the junctions. So we should say we have the common criteria is to maintain the velocity of the pipes above 0.6 meter per second. This is for the smaller velocities are lead to bigger diameters. So we have to avoid the small velocities, and also we have to avoid the higher velocities, more than 1.5. Well, that's because of the scouring. So the main purpose of or analysis point, the criteria is one in the design or analysis in our network. Should we have the velocity will stay in the maintain in this range? The velocity will be more than 0.6, and the velocity it will be more than 1.6, and it will be more than 0.6. Now meter per second. This is the first one. The second one is to maintain the head loss. The head loss over the length of the pipe. What I mean by the head loss, if I have a pipe here, and we have the flow inside this pipe like this, okay? So the direction of the flow is to be here. Like this one, it's a Q, and we have, for each Q, we have a V velocity, and we have the diameter of this pipe. Now, for each point, we have here the pressure. So if I have a point, 2 points like A and B, and as you took in fluid mechanics, we have the pressure at A and we have the pressure at B. Now, dividing pressure by gamma, it will give you head. So this is the head at point A, and will be the head at point B when I do head at point B. Now, if the distance between A and B was L, this is the L, so the head, will be head at point A, and will be head at point B, and I know that you know what is the head. The head is from the Bernoulli equation. Bernoulli equation say that the pressure at any point is equal to elevation head plus pressure head plus velocity head, right? So elevation head, it means Z1 plus pressure head, it will be P over A gamma Z1 and V A square over 2G. This is the Bernoulli equation. For B, we have the pressure at B divided by gamma, then the ZA here, this is ZP, and we have velocity at B square over 2G. Usually the velocities are the same, so they will be, let me say, it will not affect on the pressure head. And if the Z they were in the same level, then it will also cancel it out. So still we have just the pressure will affect on this one. So the head at A and the head at B and detecting each other, or let me say they should be equal to each other. But because of there will be head losses, so head pressure at A minus the head loss from A to B will give you the head at B. Now, if I want to draw this point, this is the head at point B. This is the head at point A. So the head, the difference between the two heads, the two energies, this is HA minus HB. It will give you head loss. Head loss, this is the HL between A and B. Okay, now dividing this head loss between the length, this should be between 1 to 3%. You know that will be measured in meter. This is also in meter. So dividing the head loss by the length will give you a percentage, or it shouldn't be more. The head loss shouldn't be more than 3%. If you have more than 3%, it means that the head losses through the pipe will be very high. So what should you do? You should decrease that head loss. It means that you should either to change the pipe diameter here or do another thing, or let me say add a pump, or let me say you have to decrease the diameter and so on, because we have to see whether the pressure is within the range or not. So these are the two main criteria that we are using them for the design criteria. Besides of that, the pipe's diameter should be within the 100, 150, 200, and so. These are standard diameters, and don't forget that for each certain type of pipes, we have a specific diameters. Maybe for ductile iron pipes, we have a specific diameters, and the one that we are using it, if you have a pipe like this, so in hydraulic design, we are going to, this is the hydraulic design. If this is what the cross section of any pipe, so what we have here is the diameter, and this is called inner diameter, and this is the thickness T, or thickness of the pipe. Now look at the thickness of the pipe. This is the thickness of the pipe, and this is the inner pipe. So when we are going to analyze for the flow in this pipe, if we have a Q, we should just divide this Q by the pi d squared over 4. What d? The inner diameter, not the outer diameter, because the inner diameter will be the effective diameter, or the effective cross section of the point. These are all general points that we need to analyze. Now, the head loss from A to B, that will be here. We have an equation for calculating the head loss. This head loss will be founded through two main equations. One of the main equations that we have, and remember that we say this head loss, and by the way, it's called slope. S, it means the slope. S, this S is the slope of this line, and this line is called hydraulic gradient line. So the hydraulic gradient line slope will be head loss divided by length of the pipe. That will be 1/3. We have two equations. We have two main equations for calculating the head loss. You know that as much as you have diameter, there will be much head losses. As much as you have the pipe was more length, having more length, it will be we will have more head losses, and so on. So the two equations, or the most common two equations that we are using, is one called so the head losses will be calculated by using two methods. One first method. Sorry.
Darcy-Weisbach equation.
Weisbach equation, and
Hazen-Williams.
Yeah, which is say that the head loss will equal to F L over D, v square over 2G. And remember that if you want to change this velocity to make it as a cube,
Isn't it for 4v squared over 2g.
Yeah, we are using, yeah, some of them are using this one, 4 over 2g, and this 4f, usually we are using just f. For the pipes, they are using 4, and I think in the equation we have 4, right? Usually the Darcy-Weisbach was for the open channel, so 4, it means 4 L over D. It's okay to use that for. So 4, this is for
I
closed.
think this one is for the pipes.
Yeah, for the closed pipes, we have 4. But for the open channels, we have only FL over D V square over 2G. Okay. Now, when we are using this equation, we just make a somehow simplifying this equation. I mean by simplifying the velocity. Usually the velocity is equal to Q over A, right? Which is equal to Q over area is equal to pi d square over 4, right? Am I right?
Yes, sir.
Okay, so the
Yes,
head
sir.
loss is equal to F L over D V square over 2G, which is equal F L over D. Instead of V, I will use this equation, which is Q over pi D square over,
After we forgot the 4. We
right?
forgot the 4.
Sorry.
The 4 and before the F.
Yeah, I know. I know that. Just let me finish. There is a 4 here. Okay. And divided by 2G. Right? So this is the V square over 2G. Now, just forget about this for now. And I will tell you why we have this. So the main equation is H F L over D V square over 2G, and this is F L over D. Instead of V, we will use Q over A, which is Q squared over pi D square over 4 divided by 2G. Now, what we will have F L over D, and we will have, will be 2G, will be Q squared, and there will be again 1 over pi d square over 4 again square. Pi square with 2, it will become 1, it will be 16, right? Over here 16, and pi square and d power 4, right? So we have this term will become like this, and we have Q squared, we have 2G, and we have L over D, we have F. I think that the main equation will come with this one. Yeah, so this is what we will have. The head loss when we are using yeah, I think we have a problem with the F. Yeah, there should be 4, right? Something wrong with that 4. I don't agree with that, having 2 4 here. Anyway, yeah, then this is first equation. The other equation is, this is the Darcy-Weisbach equation. The other one is called William Hazen. So Darcy-Weisbach dW, and we have William Hazen. William Hazen just excuse me just 1 minute. Again, I'm sorry. So this was the first equation. The second equation, we have the William Hazen formula. And by the way, those peoples are just, this is what we have. The William Hazen are just like a Manning equation and Chase equation. This person are acting on an equation that will give a velocity in a pipe. So the velocity, say that the velocity will be like equal
0.355
yeah.
C.
Yeah, that's right. The William Hazen is 0.355 C, and this is the equation of this one person. 0.355 C, which is, this is a constant, and this constants belong to William Hazen constant, which is will be depend on the type of the pipe. For example, a new pipe, a new high-density polyethylene pipe, we are using a C value as equal to 150. And whenever you want to buy, or whenever you want to buy a type of material or a pipe, you have to ask whether this pipe's William Hazen constant is how much. They will give it to you with a catalog. So it will be in terms of between 100, and if we have an old pipe or a non-active pipe, it will be less than the 100, maybe 80, maybe 75, we don't. This is one. So we have this C. And look at the D will be in terms of meter. For example, if you have a pipe of 500 millimeters diameter, so what should you substitute here? You will substitute as a 0.5. Okay, the S is unitless, by the way. We say that the S is equal to the head losses between the 2 points divided by the length of the pipe, which this is what we say that it should be between 1 to 3%. And it's unitless. And you have to see what are these powers are coming from. They are coming from this is empirical equations. When you substitute the D by in terms of meter, you will get the V in terms of meter per second. Okay. Now this is the velocity, and multiplying the velocity by area of the pipe, we will get a Q, right? So just pi d square over 4 times 0.35 C and times D and times S will give you an equation. This is the equation of the flow. Using William Hazen equation. And because we are engineers and we are not most interested in the equations, there is a nomograph. What is the nomograph is this: you have an equation which have S, D, C, Q, okay? So some persons or some guys are coming and putting the value of Q and the values of D, and they found it, the S related to these values and so on. So they come with this chart. This chart is telling this nomograph, this is called nomograph. Can you see this nomograph?
Yes, sir.
Yeah.
Sure.
This nomograph is basically it is the same equation, but this equation now you can use directly this one. You can see here is written flow, which means the Q, and the flow in gallon per minute, GPM, and this is in your left hand. In your right hand, there are also this belongs to Q, but it's in terms of what? Liter per second. So liter per second, the flow in the cubic meter per second, you can just multiply this liter per second by 0.001. So this number, when I said I have a Q, for example, if I say I have a Q is equal to 150 liter per second, okay? And I have the diameter of the pipe, for example, I have a diameter of 10 inch. Okay, I want to see how much is the velocity using the William Hazen nomograph. The pipe material is as C equal to 100. Now, First of all, you have to start with this C. Is this nomograph belongs to that pipe or not? So if you see that there is C equal to 100 and this is C 100, then I'm in the correct William Hazen nomograph. Now after that, I will go with the Q, which is equal to 150. Where is the 150? This is 10, 15, 20, 20, 30, 40, 50, 60, 70, 80, 90, 100, 150. And this is logarithmic scale, by the way. So this point is, this is first point, this is the Q equal to 150. And you have to take the right hand point readings as they are in liter per second. Now, the second line is the pipe diameter. Here's the pipe diameter, which is the D. In the D, you have either it will be in inch or it will be in millimeters. Which one you can use them? You can use any of them. So I'm using with 10 inch, so you don't need to convert that inch in millimeter because this is the 10 inch direct. And if you want to change it, it will be go in 2025. Now, what should I do with these 2 points? I will just draw a line. Let me, the line should be in another color, this one. I will start doing a line between, I will start with this point, with the 150, and I will go with the, with the 10 inch. Okay, then I will do like this. What should I do after that? I will just extend this line. Extending this line to see where it will be the interconnection between the extending line with this one. So it means that you will start, after this you will start to see where it will be the intersection. Okay. Now, can you see where is the this point? This will be the velocity. The velocity of the flow in the pipe, which will be in terms of what? In terms of sorry. Here's we have two things. First, here's will be the velocity in terms of feet per second, and or in terms of meter per second. It will be the same. So if you want to just find in terms of meter per second, you will take the readings of right hand. And if you want to just see in the feet per, and what is this one? This is the value of S, which is the head loss divided by length. So there are four things. We have Q, diameter, S, and velocity. Whenever you have two of them, you can get the other two ones. We are considering that we are taking one C value, okay, for C set. So having every 2 ones, you will get any other 2 ones. This is in case that you are in hurry. You have, for example, 500 pipes in your network, and you are you want to check and without using the equation 500 times. And then nowadays we have Excel equation, you can use that one, but this was innovated in the early 900s. This is the
Doctor,
other one.
this is, excuse me, this is mostly used for drainage calculations, right?
No, this is just for water, by the way. This shouldn't be used for drainage. This is William Hazen. Yeah, the other one that you are talking about, this is William Hazen nomograph. The one that you are talking about, we have another nomograph that's called Manning nomograph. Manning nomograph is say that we have 5 lines, by the way. The Manning, we have the Q and the diameter, and we have will be a line. We have N, we have I think it's velocity, or it's velocity and something like that. So you have 2 and you will take those two readings and you get here, and then you have to reflect which value of the n, and you can get this one. So this is a pivot line. This is Manning equation. It will be used for sewers. Why? Because Manning is said that we have V1 over N R 2/3 S over 1/2. This is for partial flow. We say that there is a difference between the sewer and the water distribution pipe. The water distribution pipe usually should be fully flow. While for the sewer, it shouldn't be fully flow. We have to leave some area, some space for the gases and for the anaerobic conditions to make it aerobic, not anaerobic. And we have Manning and Chasey equations that are for partially flow and for sewers used. We have William Hazen and Darcy Weisbach are used for the water. This is the difference between those two numbers. Okay, is it clear?
Thank you very much. Yes.
Yes, have fun, right? Now, based on this one, I have a simple, simply we have a network, which is very simple network. I want you to find this is what in this network we have A, B, B, B prime. This is A. This will be B, and there will be A, B, B prime. And there will be a BC. There will be BCC C prime. A will be BC C prime. AB BB prime. BC CC prime. CCD. And we have DCD DD prime. And DD prime, and we have D. Now we have this network. This is a pipe network. Any network in water network, we should have a pipe. These are the pipes, and this is called junction. Junctions or node. Now, what is required? Required to have pressure in the nodes. Should be within a limited, shouldn't be less than specific numbers, and this specific numbers different from city to another city. But in here in Siamania, we are using the pressure at each point shouldn't be less than 2 megapascal, 2 bars or 20 megapascals, and so on. Now we have, and usually when we have, let me say this is people are living here, so I can say this is for there are houses here. So by the way, these are the main pipes. So I designed for the main pipes. Now the flow, the Q that these pipes are needed, it will be considered the flow from this one. So for example, if I have 100 houses here, you should multiply the 100 houses by the number of the people that living in that 100 houses. For example, if you want every house having 6 people, times and the average demand for each person is 250 liters. This is the average demand. The design should be based on maximum daily plus fire. This will be the Q. The Q that we need to design this network for, it should be considered as how much is the maximum daily. Maximum daily is equal to average daily times 1.8. We know that this 1.8 is 15 factor. Plus the fire. How much is the fire? We see that we have 2 equations for the fire. Either it will be based insurance service formula and national formula, national NBF, national board formula. This will depend on the area of the multi-stories, the 18C square root of A, and this will depend on the population. 100,020 square root of the p times the 1 minus 0.1% of the square root of the p. So we have Q of the maximum daily plus the fire. So maximum of daily plus the fire or the hourly, this is will be considered for the main feeder. Where is the main feeders? The main feeders, here's the main feeders. Where is it? Can see. Got this. The main feeders here, these ones are considered to be these are main feeders. Main feeders, it means the main pipes. So the main pipes, we have lateral pipes. So for these pipes, the main feeders, we should consider either the maximum of Q, the maximum daily plus Q fire, or Q maximum hourly. So which one will give you for the area that this pipe will consider? For example, let me say this area will be, there is a houses here, so you should find the Q maximum day for this area and fire for them and see how much it will be equal to, and find the maximum hourly for this area and compare between them. So the flow in this pipe should be based on that one. And for the main one, or for the lateral pipes, you just consider the Q fire. The Q fire, it means that if there is a fire in this area, how much it will be the Q. And then this will be the demand for that. This is the same thing here. We have the main pipe circle. For example, if this main was Slimania, if we have a ring rod in Slimania, so we have a pipe ring rod like this one. So you have to find the people inside this city, in that is living inside this ring rod, and then for calculate that I have maximum daily demand plus the fire demand for those people here, or this is will be the calculator and put it in a side, and then find the maximum hourly demand for those people without any fire. Then which one will give you the maximum? It will be considered that the Q should be here, this Q. And for the laterals, the distribution pipes here, the pipes, the Q fire will only be considered. Most of the engineers are, they will make mistakes when they are going to calculate the diameter of the pipes. They will just say, okay, I have a house here, how much is the population for this house? So the Q will be like this. No, the Q will not be for the distribution pipes here, will not be based on the people living in this house, because it will give you very little flow, and the diameter will be in terms of millimeters. Now this is a wrong thing, and you have to calculate the Q5 for that house. This is will be very, this is what is the scientific way. And also here, we have the main pipes. Here is the main, and here's the lateral. Back to our procedure. The procedure is, now we say that we have this one, A, B, B prime, C, C prime, D, D prime, E. So the pipe diameters are given to you, length of the pipes are given to you, and the Q. I mean by the Q, when I say that we have for DE 7,500 liters per minute, this is DE, it means the flow in this pipe. It will be 7,500 liters per minute. So be careful that this liter per minute should be changed to liter per second for meter cube per second for our calculations. When if you have using William Hazen or other equation. Now, what is the required? The required is that we have this network and we have an elevated tank at A. Elevated tank at A, it means there is the pressure, the water have a pressure at A. How much is the pressure? When we have a tank here of 20 meters high, 20 meters high, it means that the water have a pressure here head of 20 meters. So HA is 20 meters. Now, how much it will be the head at B? It will be head loss at A minus the head losses that will be from A to B. So how much is the water will lose energy from A to B? It will be HA, HL from A to B. Then it will be HB. Okay. Now, in this space, here's the first of all the length from A to B and the flow. By the way, you can see there is the flow for AB is not given here. I think it is not given here. Oh, it's given here. How can we check this one? The flow from A to B should be equal to the flow from BC and BB. What that means? That means the flow here is 20,000, which should be equal to the flow in this pipe and the flow in this pipe. Why? Because we have the QAB, and this is QBB prime and QBC. So the mass momentum equation or the continuity equation is say that the QN is equal to Q out. How much is the income? The income it should 20,000. It should be equal to 4,500 here and 50,500 here. If you have these values not, if it's not checked, so we have something wrong with the network. You should check. So first of all, you have to check the continuity equation. This 15,500, it will should be equal to 3,500, yes, plus 12,000. So the addition or the summation of these two values should come with this one. So Qn is equal to Q out. Qn is equal to Q out. And so now after that, after you are checking the Q, you have to make it in liter per second. Okay, I will assume a diameter. Diameter assumption for the diameter, you have a list of diameter starting with 100 millimeters on going forward. So you will assume, and by the way, this is, in this example, it was in inch and just I converted to millimeter. But I'm just assuming the diameters based on my experience, you can do it. Any assumption, you are free to do it, but you have to check that assumption. Now, I assume that the diameter of pipe DE, where's the DE? This is the D and E. I assume this pipe is equal to 250, how much? It was 262. 262 millimeter was my assumption to have this flow, the diameter of this pipe. Now, you have the Q in this pipe and you assume the diameter of this pipe by 262. So you have the length of this pipe. So what should I do? I will find two things. I will find the velocity in this pipe, which is Q over area will give you a velocity. And I will check whether this velocity in this pipe, and by the way, this is a tree distribution. It will be very easy to check and analysis. So I will check whether this velocity is within the range or not. And let me see the area. If you have this one, it will be the area of this pipe here, and the velocity, which is equal to Q over A, which Q? This Q divided by this area. So it will be the Q divided by area will give you a meter per second. This should be between 0.6 to 1.5 meter per second. Now we have a value more than this one. It means that your assumption is wrong, or you have to do something with that D. After finding the velocity, you have also to check the head loss in this pipe and check the S. The head loss in this pipe, here's the head loss in this pipe. The head loss, it should be between this and this point. So what should be? We should find the head loss, because we are using, say that use, here's the, sorry, the level of is 20 above ground level, and you have a minimum residual should be 6 meters. Require the flow on the
Doctor,
yeah.
can you please solve this example step by step? Because
Yeah.
it's
Yeah, I'm just giving you. We will start solve it step by step, but I'm giving you a just overview, and then we come back by step by step. Now, let's solve it step by step, as your colleague said. Now I will do. Was the. I will first of all I will do a table. Okay. What I will do first of all, I will draw a table. This is the table. I will say pipe length Q. Okay. First of all, what will be the pipe? First pipe is A to B, right? This is A. How much is the length of this pipe? This is 400-meter pipe, right?
Yes,
Hello?
Doctor.
So this is 400, it will be in meter, 400 meters. How much is the Q in this pipe? It's 20,000 liter per minute. 20,000 liter per minute. And let's change this liter per minute to make it in meter cube per second directly. So liter per minute, it means 20,000 liter per minute times 1,000 liters meter cube. And what about the minute? We have 1 minute is equal to 60 seconds, right? So minute with the minute and liter with liter. So any value of L times divided by 60,000 will give you a meter cube per second. Am I right? So first of, this is will be Q in meter cube per second is equal to Q times 1 over 60,000.
The first one is 0.33.
0.33 meter cube per second. Now, okay, we have to assume a diameter. And we said this assumption, you have to check it later. Let me show you some experiences because this is the main pipeline. The main pipeline here should be the greatest one. And there will be like this. This is all the main pipelines. So these pipelines are usually having the greatest load on them. So based on my experience, I will use, for example, the pipe of 10-inch. A pipe of 10-inch, which let me just unify with my assumption in the lecture. I just assumed AB as a 514 millimeters. 500, let's say. So I will assume 514 millimeter. This is my assumption. 500 means half a meter. 50 centimeters will be the diameter. Now, how much it will be in inch?
Divided by 250.
Yeah, 25.4. 514 divided by 25.4. It will be 20
Yes.
inch. 20 inch. Now, I assume the value, here's the value, and I will check with the, I will find the velocity in this pipe. The velocity in this main pipe, which is here, this one, it should be equal to Q of this pipe divided by the diameter, the area of this pipe. The velocity is equal to Q divided by area, okay? Now, before that, let me just find, and why I am doing this, because I have to find the area of the pipe, and then velocity. The area is equal to pi d square over 4 for each pipe. So pi d here is 0.1540 square over 4, which is equal to 3.40 times 0.514 square and divided by 4. It comes
27.
27.4 meter square, right?
Yes.
And then the velocity now, it will be how much? Just dividing this value and the Q. So velocity is equal to Q divided by area, which is like 0.33 meter cube per second divided by 0.20704 meters square. And this is will come as 0.33 divided by 0.2074. It will be 1.59 meter per second, which is somehow good. Okay. Now there is another thing to check, and the head loss. How to find the head loss in this part? If I'm using this equation, so I have to have the value of F. Okay, the value of F, this Froude number, it means the pipe that we are using it. You have to know how much is the roughness of this pipe, and the roughness, it means the E over D of this pipe, and also the Reynolds number, rho VD over mu. From these 2 points, you can get the value of F, which is 0.01 to 0.02. Okay, this is one. You can use that one, or I will give it the value of F directly. This Darcy-Weisel. I will say assume the value of F is equal to 0.02. This is only. So if you want to just find this one using the fluid mechanics that you have it, you have to use the Moody diagram. From the Moody diagram, you have to have the roughness of the pipe, or you have to check, first of all, you have to check is this is a laminar flow or a turbulent flow. How to know it's a laminar? By finding the Reynolds number. You have raw water, which is 1,000 kilogram per meter cube. Velocity is this one, which is 1.59, d diameter, which is 0.514, divided by mu. If it was more than 4,000, it means this is a turbulent, and you have to fix that one, and you have to find the roughness of the pipe divided by the diameter, which is 540, and from those two ones, you can find the F, and I think I have it. Let me show it to you. Yeah, can you see this one? This is called Moody diagram. You can see. We have the pipe. For our case, we have, for example, cast iron pipe. For cast iron pipe, the E is equal to 0.15. So dividing this E by the diameter of the pipe, which was 0.500, I think 524 meter.
14.
14. This
14.
meter, yeah, this is meter 0.15. This is millimeter. Okay, this is millimeters, and when you want just times minus 3, you will see this will be E over D. So 0.15 divided by 0.5, how much it will become?
It's 2.91 multiplied by 10 to the power minus 4.
0.259 times 10 to the power minus 3, right? So
no, it is 0.29.
0.29, sorry. It will be 0.29 times 10 to the power 9. And when can I find this number in the E over D? 0.259, or it will be 3 times 10 to the power minus 4. 3, this is 5. This somehow it will be here. Okay, it is, well, it will be within these two lines. Now we have to find the Reynolds number. The Reynolds number is equal to rho VD over mu, right? So rho is 1000 and V is 1.59 times diameter is 0.51 times this will be 1 times 10 to the power minus 3. Think something high like this, and we will consider that we have these two pipes, and if I'm working on the, even if we have in the turbulent, here's the turbulent, it will be more than 4,000. So the more than this 4,000 is here.
It's 81,000.
Yeah.
No.
In worst condition, we have the value of F will be here. It will be 0.0 less than 0.02, and it will be mostly within this one. Yeah. You can see it will be ranged between 0.01 till 0.04. This is in a worse condition. So the value of F, you have to put it in your, so 0.01 to 0.04. I will use the least one because I want to see, sorry, I will use the highest one to see the maximum head loss in this one. So I will come back with my, I will use the F as equal to 0.04. Okay, now what will be the head loss in this pipe between A and B, considering the F as equal to 0.04? I will just apply this equation. This equation, the head loss is equal to, let me say it's equal to 4 times, this will be 4 times F, which is 0.04, times the length between pipe A, and by the way, this is if you are using Darcy, you can use this one also. 0.04 times the length from A to B. Now we have 400 meter. Here's the 400 meter. Times what left? 4FL V square. Now V square is 1.59 square over how much? 2 times 9.81, which is G, times the diameter. This phi is diameter. The diameter is 0.514. So this will be in meter square per second square, right? This will be in meter per second. So the second is second square is we have meter per second square also. Okay, so secant square with secant squares will be this one. The 400 is in meter. Yes. And this is not meter, this is only meter. Meter per second square, this is meter square per second square. So second square with second square is cancelled out. Meter square with meter. So this is will be cancelled out. So what we left, there will be just 4 times F times L. So this is will be the head loss between A to B.
It's 16.04 meters.
16.04.
04. 04.
04. And I think this is wrong because this we don't have that for. I will check this one. I will check that one. I don't have this one. I'm not sure about that form, by the way. Okay. Okay, let me say if this is was 16.04, we will go with that error. So the head loss, this is will be the head loss for between A to B. Now, 16.4 meter is the head loss. Means what? Means the slope means that the S is equal to the head loss that we have, 16.4 divided by what? The S is the hydraulic radiant line slope, which is equal to head loss divided by the length of the pipe, divided by the length of the pipe, which is 400. And now it is equal to how much? 16.4 divided by 400.
0.04.
0.041, which is equal to 4.1 percentage. And also somehow this is high. This shouldn't be 4, it should be between 1 to 3. Okay. Anyway, now how much it will be the pressure at B? The pressure it will be the pressure at A minus this head loss. Now the pressure at B is we have the pressure at A, which is 20 meters, minus the head loss from A to B, which is 16.4. Now that means we have 3.6 meter is the head at point B. Now this is the head at B is 3.6. Now what should I do? I should do the same calculation, find the head loss from B to B bar. I have its length, I have to assume the diameter here, and I have to find the velocity in this pipe here because I have the Q in this one, and check the velocity and check the head loss using the same equation and check the S.
Doctor?
Yes.
I think the problem is in the F. If we make the value of F in the head loss equation to be 0.01, we'll get a head loss of 4 meters and not 16 meters.
Yeah, well, I'm not sure about this for, but I will check it later.
I've calculated that for as well.
Yeah, so yeah, the F in worst condition we are using 0.04. Anyway, this is a design procedure. You can just change the diameter. For example, I will use another diameter. I will use the 600 millimeter diameters. Okay, just having more diameter, the velocity will be decreased and the head loss will be decreased, and you will get that. But this should be based on the approvals, not by yours. Okay, because any extra diameter and extra diameter will make more cost. So if you want to make the design perfect, you have to change the diameter, so it means that it will cost more than what you did. So in this case, you have to make a kind of reliable or minimum cost design. This will be the your rule. It will be appear here. You want to do a design with the least possible cost for the diameters. Smaller diameters means less in cost. Higher in diameter means high in the cost, and so on. Is it that clear to you?
Yes, doctor.
Ali, was it clear, right? Now I will stop here right now and we will continue this example tomorrow.
Sir, I'm here.
Okay, Ali, thank you.